The man who invented trigonometry and first scientifically cataloged the stars' positions to be used for celestial navigation was Hipparchus of Rhodes, an island in ancient Greece. Hi, my name is Tom Atwater, and today we are going to be investigating trigonometry. Let's start by defining some terms that are necessary for trigonometry. Trigonometry takes on a more dynamic view of angles by thinking of the angles in terms of a rotating ray. This ray is referred to as the initial side, and we're going to rotate that ray through an angle alpha to its terminal side. And the measure of the angle is the number of degrees that it turns through, and we measure the angle as a rotating, for positive ones, rotating counterclockwise. For negative angles, as this one is, here's my initial side, and now I'm rotating it this way over to here, and that's rotating clockwise for negative angles. An angle in standard position is on the Cartesian plane, and it has the vertex at the origin, and the initial side is always lying along the positive x-axis. Coterminal angles have the same initial side and they have the same terminal side, yet they have different measures. And we're going to try that out on this problem. Find and draw a positive angle and a negative angle that are coterminal with the given angle. And let's take A. First of all, the 30-degree angle, we lie the initial side along the positive x-axis and then rotate it through a 30-degree angle. And now, what we were interested in is finding another positive angle that is coterminal with this. And what I could do is simply go around this once and then the additional 30 degrees like that. Remembering that once around is 360 degrees, we can now say that this angle in red is 390 degrees. What about a negative angle? All right, for a negative angle, what I would do is, remember, I would go clockwise for that. So I would start here and go around this way, stopping there. And in that case, basically, I'm stopping 30 degrees short of 360, so I would have negative 330 degrees. And so my two angles that are the same as 30, in this case, I have 390, negative 330. Now let's do the negative 150. Negative 150, so I start on the positive x-axis and I come this way 150 degrees. So that's my terminal side of the angle. So I'm interested in a positive angle. So a positive angle, I would start here and come around this way, and that would bring me 210 degrees. And I can get that a variety of ways. 210 plus 150 is 360, so I know that that works. Or I can remember that this is 180, and this little angle in here is 30, so adding them together gives me my 210. Well, what about a negative angle? Well, in that case, what we're going to do is we can go around one complete turn and then continue around again. And in that case, we add the 360, or the negative 360, to the negative 150, and that would give me a negative angle, negative 510 degrees. All right, so let's do part C. Part C is 2 pi over 3. So, starting, again, the positive side, and I'm going to come around to here, the equivalent of 2 pi over 3 radians. And then draw my terminal side. So in order to get a positive angle, what I would say is, let's go around once and come back full circle, so that what I have is my 2 pi over 3 plus another 2 pi. And that ends up giving me 8 pi over 3. Well, what about the negative angle? Well, the negative angle, we would simply start here and go in this direction. And I can get this a variety of ways as well. Remember, coming over to here is the equivalent of negative pi. And then I go an additional pi over 3. So that's negative 4 pi over 3. And those are my two coterminal angles for that angle of 2 pi over 3. Next, we're going to define the 6 trigonometric functions of any angle. And the way we'll do it is we're going to start off and say, let theta be an angle in standard position, and let P of x comma y be any point on the terminal side of the angle, except the origin. Let r denote the distance from that point, x comma y, to the origin, i.e., that means that r is going to be equal to the square root of the quantity x squared plus y squared. In that case, the 6 trigonometric functions are defined as follows. Sine of theta is y over r, cosine of theta is x over r, tangent is y over x, where, of course, x is not equal to 0. And then we have the reciprocal functions that you can see as well. So let's work an example where we use these definitions. Let's take the point P, which is 5 comma negative 2, and that's on the terminal side of the angle theta. We want to evaluate the 6 trigonometric functions for that value of theta. All right, so we know the point 5 comma negative 2 would be approximately right here. And if we draw a right triangle, it would look like this, where we know this is 5 and that is 2. And we can calculate r, which we were given the formula for, which of course is the square root of x squared, or the sum of x squared plus y squared. But also you realize that just comes from the Pythagorean theorem, where we have 2 squared plus 5 squared would be equal to r squared. So briefly, r is the square root of 5 squared, which is 25, plus 2 squared, which is 4. So r is the square root of 29. So now we have all 3 parts of the triangle, and we can now actually apply those numbers to the 6 trigonometric functions. So what I'm going to do is get to a bigger screen so that I can do all of them. Remember that this is my x, this is my y, and we just calculated r to be the square root of 29. So sine of theta is equal to y over r, negative 2 over the square root of 29. Cosine theta is equal to the x value, 5, over r, square root of 29. The tangent of theta is equal to y divided by x. So that's going to be negative 2 fifths. And my reciprocal functions literally are the reciprocals, which is to say cosecant theta would be square root of 29 over negative 2. The secant of theta would be equal to the square root of 29 over 5. And the cotan of theta would be negative 5 over 2. And those are my 6 trigonometric functions for that angle who has a point 5 comma negative 2 on the terminal side. In that example, we were given a point that was on the terminal side of the angle. Let's look how to handle a problem when we are given the angle but no point. In that case, if you want to evaluate the trig functions of what we call a non-quadrantal angle, one that doesn't fall on an axis, first, draw the angle theta in standard position, being careful to place the terminal side in the correct quadrant. Without declaring a scale on either axis, label a point P, other than, of course, the origin, on that terminal side of theta. Then, draw a perpendicular segment from the point P to the x-axis, determining the reference triangle. If this triangle is one of the triangles whose ratios you know, label the sides accordingly. If it's not, then you'll need to use your calculator. Use the sides of the triangle to determine the coordinates of point P, making them positive or negative according to the signs of x and y in that particular quadrant. Use the coordinates of point P and the definitions to determine what the 6 trig functions are. Let's work an example of this. Let's say that we want to find the following without using a calculator: the sine of negative 210 degrees. And then we want to find the secant of negative 3 pi over 4. All right, I'm going to give myself a little bit more room because I need to draw a diagram. And in this case, I would have for sine of negative 210. What happens is I start here and bring my angle all the way around to here. And then I just label some point, P, and I drop my perpendicular. So this is my reference triangle. In particular, this angle inside here is 30 degrees, which means it's my 30, 60, 90 triangle. In that case, we know that the shorter side is 1. We know that the median side is the square root of 3. And r is equal to 2. Now, in terms of the point P would be negative radical 3, comma 1, as determined by the sides of the triangle, right? So now we know the point P, we know the value of r, and we want the sine. And sine is equal to y over r, so sine of negative 210 is the y value, 1, over the r value, 2. Let's do the same thing for negative 3 pi over 4. I'll draw my axis. I want to draw my angle negative 3 pi over 4, so it starts here, and it comes around this way. And now when I drop my perpendicular, I realize that this is a 45-degree angle. And so in this particular case, we know that the sides are 1, 1, the square root of 2. And so we want the secant. Now remember, secant, which is the reciprocal of cosine, is r over x. R is the square root of 2. Oh, you know what? I got to label my point. Sorry, I didn't do that. This point is negative 1, comma, negative 1, right? So now when we go to do the secant, it's r, which is the square root of 2, over x, which is negative 1. So the secant of negative 3 pi over 4 is negative the square root of 2. And that is the secant then of negative 3 pi over 4. Now, if the terminal side of the angle were to lie along one of the coordinate axes, then it's called a quadrantal angle. And it wouldn't form a reference triangle. And I'll show you that in a moment because we're going to look at how to find the trigonometric functions for those quadrantal angles. We want to find sine theta, cosine theta, and tan theta for the following given angles. If the value is undefined, we would write undefined. And let's start with the negative 450. We draw our axis. And then we draw negative 450, which would start here. We would have to go around once which is 360, and then go an additional 90 degrees. And that would be negative 450. Well, what's interesting about this is, yes, we don't get a reference triangle, but we do know that this lies on the axis, and we can label that point, for instance, 0, negative 1. And when we do that, if we then want to find the trig functions for those angles, all we need to do is use our y and x values based on that. And so let's take a look. We were trying to find all three, sine, cosine, and tangent. So the sine, right? The sine of theta is going to be equal to, or the sine of 450, since I know the angle, is going to be equal to the y value. And what is the y value here? Negative 1. Over what would have been the r value. If you think about that, what does that really mean? Well, we didn't come up with a triangle, but if you extended the idea, you could see that this is the terminal side, and it has the same value in terms of a distance as the absolute value of the y value. In other words, it has a value of 1. Now, the cosine of negative 450 would be the x value of 0. What about the tangent? Well, the tangent of negative 450 is y divided by x. And in that case, it's going to be negative 1 divided by 0, which we can't do, and that's where we put the undefined. So those are our three answers for sine, cosine, and tangent of negative 450, negative 1, 0, and undefined. Now let's take a look at the 7 pi. 7 pi is a positive angle. So once around is 2 pi. Around again is 4 pi. And then we keep going. That's around again for 6 pi. And then finally, once more, brings us to here. Now, what's the point? Negative 1, 0. That's the point where we end on that particular axis. So now, when we go to do our sines, cosine, and tangent, the sine of 7 pi is 0. The cosine of 7 pi is going to be negative 1, right? And now the tangent of 7 pi is going to be y over x, which in this case is 0 over negative 1, or in other words, it's equal to 0. So actually, finding the angles of the quadrantal, or finding the trig functions of a quadrantal angle is fairly straightforward once you realize that you can still label those points that fall on the coordinate axis. Now, let's work an example when we know the value of one of the trigonometric functions and we're asked to find the value of other ones. So here we have find, without using a calculator, the sine of theta and the tangent of theta if we know that the cosine of theta is equal to 2/3 and we know that the cotan of theta is positive. All right, well, what does it mean to tell us that both the cosine is positive, it's 2/3, and the cotangent of theta is positive? It's important because that tells us it's in quadrant 1, because that's where both cosine and cotangent are positive. So we know we have an angle in the first quadrant, and we know that if I draw a triangle, that this side is 2 and this side is 3, because the cosine is the x value, 2, over the r value, 3. We can calculate the missing side by using the Pythagorean theorem. We know that 2 squared plus the missing side squared is equal to 3 squared. Or in other words, this side is equal to, let me put it over here, the square root of 9 minus 4. So what we know is that that's the square root of 5. All right, we've got all the information we need in order to find the sine and tangent. The sine of theta is going to be the y value over the r. So the y value, of course, is the square root of 5, and the r value is 3. The tangent of theta is going to be the y value divided by the x value, so it's the square root of 5 divided by 2. And that's how you can find the trig functions of the angle without knowing the angle, because you knew one of the trig functions, and that allowed us to solve the rest of the triangle. Now we're going to explore the relationship between triangle and circle trigonometry. In order to do this, we have to first look at what's called the unit circle, which is a circle of radius 1 centered at the origin. And the way that we relate the triangle trig to circular trig is this. We have the unit circle in our picture. We have that the radius is 1 and it's centered at the origin. And then we have some generic angle t. And t refers to not just this angle here, but also it refers to the arc that is intercepted along the unit circle here. That's a measurement of t. But in addition to that, look what we've also done, which is we've taken that same length, this arc length, and we've straightened it out so that it's perpendicular to the x-axis. And therefore, this length is also equal to t. So t is a measurement of the angle in the middle here. It's a measurement of the intercepted arc. So it provides an ideal connection between triangle trigonometry and circle trigonometry. All right, let's keep going with this. And let's look at a negative angle and how that works out here. Well, it's the same type of situation. This negative angle of t still cuts out the arc that is intercepted by the initial side, because here's the initial side of the angle, and the terminal side of the angle. So that arc still gives us the length, that is the length of that angle as measured along the unit circle. Once again, you'll notice that there is this value of t here. And at this point, you may be saying, okay, why is he pointing that out? And the reason I'm pointing it out is that we sometimes refer to using the unit circle to help us with trigonometric functions. Because we're using that arc length, that it is sometimes referred to as the wrapping function. Because the arc length along the unit circle corresponds exactly to radian measure. And we can use the circle itself as a sort of number line for the input values of our functions. And that's where we get the idea of the wrapping function, because it associates a point on the number line with points that are actually on the unit circle. Let's take a look then at the trigonometric functions of real numbers, that is, using radians as our measurement rather than degrees. Let t be any real number, and let the point p, x comma y, be the point corresponding to t when the number line is wrapped onto the unit circle. Then the sine of t will be equal to y. The cosine of t will be equal to x. Tangent of t will be y over x, where x is not equal to 0. And then we have our 3 reciprocal functions. Therefore, the number t on the number line always wraps onto a point called cosine t comma sine t. In other words, x comma y becomes cosine t sine t, and we can see that in this diagram, where t is the angle here measured along the unit circle, and it terminates there, and that point, although technically is x comma y, we now know that it's cosine t comma sine t. Now, although it is helpful to draw reference triangles inside the unit circle to see the ratios geometrically speaking, this latest round of definitions doesn't involve triangles at all. All it involves is the real number t, which determines a point on the unit circle, and then the xy coordinates of the point determine what the 6 trigonometric ratios are. For this reason, the trigonometric functions, when we apply them to real numbers, they are sometimes called the circular functions. Recall that there are multiple angles that share the terminal side, and therefore trigonometric functions repeat themselves after a certain angle size. That is called the period. That is to say, the amount of the angle that it takes when it begins to repeat is the period. So let's take a look at that. Periodic function. A function, y equals f of t, is periodic if there is a positive number c such that f of t plus c is equal to f of t for all values of t in the domain of f. The smallest such number c is then called the period of the function. Well, what about the periods? For sine and cosine, the period is 2 pi, which means it takes 2 pi, a full circle, and then those will begin to repeat themselves. While the period for tangent is only pi. And what that means is once you go around to pi on the circle and then start to go around some more, you will begin to repeat the values for the tangent. Let's try an example of this. Let's say that we're going to find, without using a calculator, the sine of 57,801 pi, all divided by 2. So what you have to realize is that there's got to be some multiple of 2 pi in there. And what I'll do for you is break this up. We can say that this is the sine of pi over 2. Because notice there's this sort of extra pi over 2 sitting in there, that 1. Because now what happens is this would be 57,800 over 2 pi. And now 57,800 divided by 2, of course, will give us a multiple of pi, which is actually a multiple of 2 pi. And therefore, this portion of it just means that it is a multiple of the period of pi, which is a multiple of 2 pi. So therefore, this is just the sine of pi over 2. And the sine of pi over 2 is equal to 1. So that's how we can use the idea that it's a periodic function to find the sine of an incredibly huge angle. Well, now it's time for you to try a problem. And the problem I would like you to do is to find, without using a calculator, the sine of pi over 6 plus 49,000 pi. So pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Let's find out how you did on this. In this particular case, let me get some more room here. What you should have recognized was this is already a multiple of 2 pi. In other words, it's an even number, 49,000, Therefore, 2 goes into it without a remainder. And so that already is a multiple of 2 pi, which means sine of pi over 6 plus 49,000 pi is just the sine of pi over 6. And the sine of pi over 6 is one of the special angles that you should have memorized by now. It's equal to 1/2. So I hope that's the answer that you got when you examined that problem. Today we're going to finish by examining what's called the 16-point unit circle. And what that is all of the angles that are ones that are of the special triangles that we want you to memorize, essentially. And here is that unit circle. Let's look at some specific points. Let's take the point pi over 4. Now, pi over 4 means a couple of things. It means that the length along here is pi over 4. And as you know, that also means that the angle inside here is pi over 4, or as you saw, 45 degrees. And in that case, on the unit circle, we have the point x comma y, which is the square root of 2 over 2, comma, the square root of 2 over 2. All right, well, we could look at specific points in each of the quadrants. For example, let's say that we want to examine in more detail 5 pi over 6. Again, that's the angle can be thought of as the arc on the unit circle. It can also be this angle here. And in this case, my x and y coordinates are negative radical 3 over 2, comma, 1/2. All right, let's pick an angle in the third quadrant. Let's pick the angle 4 pi over 3. So that angle would come all the way around to here, and it would still be the length of this arc of the unit circle coming all the way around. And in this case, our x and y coordinates are negative 1/2, comma, negative radical 3 over 2. And finally, let's finish with a point that's in quadrant 4. Let's pick the point 11 pi over 6. So that would be the angle is the arc along the unit circle. This is a measurement, and that measurement is actually equal to 11 pi over 6. It also would be the equivalent of this angle drawn in standard position, and that gives us the x and y coordinates of radical 3 over 2, comma, negative 1/2. Now, what you'll notice about that is that you don't necessarily need to memorize that entire set of numbers. You should be able to use reference triangles plus the quadrantal angles to evaluate the trigonometric functions of all of the integer multiples of 30 and 45, or in other words, pi over 6 and pi over 4 radians. And all the special values wrap onto these 16 special points, but you don't necessarily need to memorize each one. You can study the diagram and get to the point where you're confident that you can find the coordinates of each of the points easily. And again, you don't necessarily have to memorize that. All right, great job in today's lesson. So in today's lesson, we explored trigonometry with respect to triangles, and we made the connection to trigonometry using triangles to trigonometry using circles. Be sure to work the exercises that your teacher assigns, and we'll see you next time.